In this video, we are going to talk about derivative. First, let's review slope. We know if we have a straight line, let's consider this to be our axis. This is x-axis, this is y-axis. Let's say we have a line, right? These are a straight line. Now, it has a property known as slope. And how do we calculate it? We take 2 points. Let's call it x1, y1. And another b, which is x2, y2. Now, calculate slope by using the formula right divided by run. This is our right, this is our run, which numerically are given by x2 minus x1 and y2 minus y1. So, slope is nothing but rise divided by run, which is equal to y2 minus y1 divided by x2 minus x1. Now, we're going to use a symbol, which is a triangle, small triangle. It is a Greek alphabet and its name is delta. And it is associated with change. It represents change. Similarly, now we will call y2 minus y1 del y because it represents change in y. Okay? And this represents change in x. As we move from A to B, how much has x changed? This is given by this part. So this is del x. And how much y has changed is given by this part. So this is del y. Now, derivative is nothing but slope of a tangent line. Okay. Derivative is what? Slope of a tangent line. We calculate derivative for a function. So, if we have a function, let's say any function like this, then if we want to calculate derivative at this point, we're talking about the slope of the tangent line at this point. So, this is our tangent line at this point. Okay. Derivative at this point is equal to slope of this tangent line. That's why we are reviewing slope first. Now we'll see how to find the derivative. Now we'll see how do we find the slope of the tangent line. Let's draw a random function first. Okay. Let's call it our function y equals fx. This is our function. Let's say we want to calculate derivative at this point. Let's call it p. Its coordinates xy. Now, if we wanted to calculate derivative at this point, then what do we need to find? Slope of the tangent line. Okay. Let's see. This is our tangent line at this point, and its slope is equal to the derivative at this point. Okay. Now, the idea here is to draw a line. First, we draw a line, random line passing through this point. Okay, and call it Q. First, we find the slope of this line PQ, and then we find the slope of the tangent line. Okay. So, for PQ, this is del y, this is del x. Now, slope of PQ is given by del y divided by del x. So, this will be nothing but x plus del x and y plus del y. Now, we want this line PQ to approach this tangent line. How can we do that? We can do that by letting Q approach P. Okay. As Q approaches P, the second line PQ approaches tangent line. In this formula, this can be done by taking limit del x tends to 0. Okay. As del x becomes 0, Q will coincide with P, and the second line PQ will convert into a tangent through P. Right. So, if we take limit del x tends to 0 and find del y by del x, this gives us what? This gives us slope, and this limit tells us the second line converts into tangent. So, this as a whole gives us slope of the tangent line. And this is our definition of derivative. Limit definition of our derivative. Now we'll see notation. How do we represent derivative? This is the most used one, dy by dx. Here it is telling us derivative of y with respect to x. This is equal to nothing but limit del x approaches 0, del y by del x. So these are limit definition of derivative. So far we have established these things. The derivative is equal to slope of tangent line, and it is given by this limit and represented by this symbol. Now we'll see what it means to be differentiable. If derivative can be calculated at a point for a function, then the function is called differentiable at that point. If it cannot be calculated, then it will be called not differentiable. That's a simple meaning of differentiable. If this limit exists, then we'll call the function differentiable at that point. If this does not exist, we'll call it not differentiable. Now we'll see relationship between continuity and differentiability. But before that, we need to understand how geometrically we can interpret differentiability. Okay. So we know derivative is equal to slope of tangent line. So if this exists, slope of tangent line exists, then the function will be called differentiable. So this means slope of tangent line should exist. Line should exist. That means if the slope of the tangent line is infinity, it will be called not differentiable because infinity is not well defined. So now this can also be stated as existence of unique tangent line. Why unique? Because if there are many tangent lines, then there will be many slopes. So we cannot find a unique value for the slope. That means the limit does not exist. Therefore, if there is a unique tangent line with slope not equal to infinity, then it will be called differentiable at that point. Now let's see relationship between continuity and differentiability. First, let's say what does it mean for a function to be discontinuous. If a function is discontinuous, then it will be not differentiable. We can show it. There will be three cases for a function to be discontinuous. Okay. Case 2, case 3. First case is if fx is undefined. Second case, if limit is not equal to fx. Fx is defined but not equal to the limit value. And the third case is limit does not exist. If these three conditions are met, then the function is called discontinuous. Now, if fx is undefined, say the function looks like this. Okay. So at this point, there is no functional value. So we need to, how do you find a tangent line if there is no point through which we want to find the tangent line? That makes no sense, right? Therefore, this will be non-differentiable at that point. But at every other point, the function will be differentiable, but only at this point, only at points where the function is not defined. Okay. Second case, limit is not equal to fx. That means function is defined, but the value is not equal to the value of limit. We can see from this graph, the limit is here and the functional value is here. So now we want to find the tangent line through this point, right? We want to find derivative at this point, so we need to find tangent line through this point. And that should be unique. But we can draw as many lines as we like through this point, right? So there is no unique tangent line. So in this case also, the function will be non-differentiable. Not the third case, limit does not exist. If the limit does not exist, we know the graph would look like this, right? So we want to find derivative at this point. That means we need to find tangent line at this point, and the tangent line should be unique and its slope should not be equal to infinity. But just like in second case, we can draw infinite tangent lines through this point. So in this case also, it will be not differentiable. That's why if a function is discontinuous, then it will be not differentiable. We saw that if a function is discontinuous, then it will be not differentiable. Now, we know that the function needs to be continuous to be differentiable, but still, continuity does not imply differentiability. That means continuity is necessary condition for differentiability, but not sufficient. Just being continuous will not suffice to call a function differentiable. Okay, for example, let's take this function. This is absolute value. Okay, the graph would look like this. This is our axis. Okay, x is y axis. The graph would look like this, right? So, if we want to calculate derivative at this point, at x equals to 0, okay, that means we need to find a tangent line through this point. We draw lines, and we can draw as many lines as we like through this point. So, there are numerous tangent lines. This means the function is not differentiable at that point. Not differentiable at x equals 0. But at every other point, the function is differentiable, because at all these points, the slope of the tangent line will be equal. So, we can say continuity does not imply differentiability. But to be differentiable, a function must be continuous. That is, differentiability implies continuity. This means for a function to be differentiable, the function must be continuous. So, if a function is differentiable, it is automatically continuous at that point. In next section, we will see how to calculate the derivative using first principle. In this section, we are going to use first principle to calculate derivative. Here, first principle refers to this definition of derivative. So, we'll use this limit to find the derivative. Now, first, let's call it y. So, that will be easier for us. In the definition, there is del x and del y. So, we need to state what these are. As say, we know del x is change, right? So, del x be a small change. Call it a small change. Change in what? Change in x. And del y be the corresponding change. So, we mention corresponding here. Change in y. This means as x goes to x plus del x, that is x changes by del x, y goes to y plus del y. So, we have function y equals fx. As y goes to y plus del y, x goes to x plus del x. We'll use this to find del y. So, y plus del y is equal to nothing but f x plus del x. So, we put the x plus del x here, and it becomes x plus del x square plus 3. Now, to find del y, we take this y and change its side. So, it will become minus y. So, del y equals to x plus del x whole square plus 3 minus y. Y is nothing but x square plus 3. So, if we now we want to expand this using a plus b whole square. This a square plus 2ab plus b square. And the remaining 3, when we open the bracket by minus, the sign changes. So, it becomes minus x by minus 3. So, these two will cancel out. And the remaining terms are 2x del x plus del x square. Now we replace it into first principle. We know from first principle, derivative is equal to limit, which is 0, del y by del x. Now we replace del y with this. So it will be nothing but 2x del x plus del x square divided by del x. Now if you put del x directly, it will come out to be 0 by 0 indeterminate form. This will always be the case. So we have to be smart and try to eliminate this indeterminate form. How do we do that? By taking del x common. So we can take del x common, so remaining will be 2x, and then this it will be 1 del x. So we have del x. So these two will cancel out. Now the indeterminate form is eradicated. So we put del x equals to 0 here. So it will be 2x. So derivative of x square plus 3 is 2x. So let's say we want to calculate derivative at a point x equals 1. We put x equals to 1 here. That is dy by dx at x equals 1 will be 2 times 1 equals 2. So if I want to calculate it at x equals 2, we'll put 2 here.